This is a dramatic reading of Deriving and Fixing the Force Equations, a blog by the Stand-Up Physicist available at science20.com. The hypercomplex gravity and unified gem Lagrange densities are wrong. Nice to hear a clear admission of error, so rare these days. My critics think that my fix is actually still broken, so you will have to be your own judge. Skepticism is a good thing. So here is the fix. That's the current coupling J, my symmetric multiplier there, and A, which is the for potential. And that conjugate operator, the star thing, is basically like a mirror, and so I'm removing a mirror. And as much as practical, I will go through my various blogs and communications and see if I can make corrections as are required. And it actually is affecting sales of these very t-shirts. So that conjugate I was saying you got to get rid of is the very first one up near the top. All right, I gotta cut it out or white it out, or, well, I'm not going to bother. I'm just not going to sell it. I'm going to wait until it's gone through a mathematic notebook or two and feel very comfortable with the solution before I go ahead and put a few $100s down to print up a new set. And it affects the front of the t-shirt. That 0 is okay for the dphi dt, second order dphi dt term, but those the 3-vector part gets a current density of Ji. And I haven't figured out all the consequences of that. But no, if you bought the t-shirts early, hey, it's a collector's item, you know, because I ain't giving any more away, selling any more that have the math wrong. That would be immoral in my sense of morality. So why did this happen? Well, like to a fault. I have hoped that my equations that are related to gravity would be super similar to EM. The current coupling term and the field strength tensor of EM are invariant under 3D rotations and Lorentz boosts. You know, and that sounded like, well, doesn't everybody have to do that? And so when I started to work on the hypercomplex product, I wanted them to have that sort of property too. And it was easy to do for the current coupling term. And that's why there's that nice, you know, conjugate on the J. It's nice, it's simple, it's direct, you know. And those conjugates are definitely needed for the field strength tensor because it has to be kind of look like a symmetric sort of operation. Okay, you see, if you don't put them on, then it looks just like the Maxwell equations, the field strength tensors, and that just struck me as wrong. You know, it can't be exactly the same and different. You know, you're either the same or you're different. So anyway, so what I did was, what I did not do actually, was to calculate how the hypercomplex field equations would transform under 3D rotations and boosts. Well, why not? It happens that there's like this big mountain of detail in such a calculation. And I did try and do it, okay? I just got lost in the mountain of detail and said, well, I hope it's right, but I didn't go all the way, you know? I mean, things like that happen. So what I did in that case, when I don't know the right answer, I hope for an answer. Well, what I did was I asked a snarky puzzle question about it. because that would force me to get the answer to the question. What happened actually was several sharp readers, they could see what the answer was. That the hypercomplex field strength tensor was totally and completely not invariant under 3D rotations, or boosts for that matter. I mean, and they were right, okay? They were rather strident in their opinion, but that doesn't matter. They were, what matters is they were right, okay? Now, it did take me about 10 days to do my own efforts and confirm those observations. So, you know, all is well and good. Although not really. Because, you know, if one term of a Lagrange density is invariant under a Lorentz transformation, like that current coupling term, and the other one isn't, well, that's actually a problem. And I didn't see the inconsistency at the time. So let me just go back a way and say, well, why have you gone on and on and on about this stuff? And it's because those are issues having to do with the forces that they were able to spot. And I was Mr. Fields, okay? And I went ahead and figured out how to derive Gauss's law for EM. I just repackaged it, okay? I mean, that's been known for an awful long time. And I've got my way for doing gravity. And you'll go, oh, those just differ in like 1 minus sign. Yeah, that's it, okay? And what does a 1 minus sign do? It means that like charges attract in one case, and like charges repel in the other, okay? The repelling is the top line, and the attracting is the bottom line, you know? This appears in Misner, Thorne, and Wheeler, you know, the gravity. Well, actually, I'm not sure if Newton himself wrote it that way or whether just French guys did, you know, but it's like, it's really, really old school about if you write that down and it's got those kinds of signs, it means definitively like charges attract, okay? Now, you know, that's the way it goes. So it's, you know, both of those equations are similar, but they do not have the same solution. I mean, they can't, right? They got a minus sign in there. It's actually one of the really cool cancellation tricks of calculus that solves the vacuum equation. In other words, del squared phi equals 0. If you've done it, you'll probably remember it because you go, wow, that was pretty lucky that we had 2 terms and that these 3 added up to cancel out that other one. Okay, it seems like magic. Okay, but it's magic that's been known since like Laplace's time, so old magic, but still pretty cool. But what's actually kind of way more tricky is to show that, you know, this charge over mass, or charge over R solution works when there is a rho, okay, when there is like a charge density on the other side. Well, it does as long as that rho is negative. Now, the way you do it actually is you do, what do? You do 1 over R squared plus A squared, okay? That doesn't, you know, blow away. And then you say, in the limit of A going to 0, what does it end up looking like? And rho is always negative. And you go, that's a problem because, you know, gravity is the other way, okay? So to get a solution for gravity actually takes more thought. And there's just this wonderful article I encourage all kind of nerds, hardcore nerds, to read on the subject by Kevin Brown, Why Maxwell Couldn't Explain Gravity. That should be enough for a Google search to find it. It's well worth the read. Maxwell was just like so sharp, okay? He wanted to treat gravity as something that had a positive, definite energy. I was like, yeah, duh. Well, the phi needed that minus sign so that like forces could attract. And he realized that by the rules of integral calculus, you know, he could staple on a huge honking value to that phi and keep it really positive, you know, just by making it huge enough. Unfortunately, he wasn't able to justify that move. So he remained puzzled about that subject to the end of his days. Now, what Brown argued was that the Schwarzschild solution of the field equations of general relativity resolved the issue, which were like 70 years later, or 50 years, I don't know when Maxwell puzzled on this particular subject. So if you look at the first two terms of the Taylor series expansion, this is what you get, okay? And that's your G00 term, okay? And, you know, that explains the big honking constant. It's big because, well, that G is really small, and C squared is really large, so it really makes that term after the 1 really, really tiny. I happen to call that that big factor of 1 the Ed Milch factor of 1. He's this old guy who goes to APS meetings talking about negative mass. It's because he's kind of channeling this issue that Maxwell knew about, and actually Maxwell solved it because he said, you know, I take the derivative of that 1, it goes away. But he couldn't justify it because it required Einstein to come up with general relativity and then Schwarzschild to come up with solutions of those field equations. So it all ties together really kind of nicely. So now that you got the 1 minus, it's like, oh, now you're going to be able to get the positive row out of that situation. So to my eye, I think I have delivered to the Science 2.0 community, as well as the YouTube folks, field equations where like charges attract. That has not changed at all, even with this this admission about the conjugate guy, because it doesn't alter the Gaussian laws. All right. Now the super tricky thing is that everything absolutely has to fit together perfectly. Kind of demanding, all right? The phi up there, you know, the 1 minus gm over r c squared, that has to be the one thing that I use in the force equations and the field equations. And I've never actually derived the force equations before. Oh, I mean, I had derived the EM Lorentz force lots of times, actually. And I tried to get to the gravity ones, but it didn't work. People are just much more comfortable with forces than field equations. You know, forces appear to be so direct. You know, good old pushing and shoving, you know, sort of thing. But there is a direct link between forces and field equations. This was in the Bible according to Purcell, Electricity and Magnetism, Volume 2, page 24. We can call the statement in the box Gauss's law because it's actually equivalent to Coulomb's force law. And it could equally serve as the basic law of electrostatic interactions after charges and fields have been properly defined. Now, Gauss's law and Coulomb's law are not two independent physical laws, but the same law expressed different ways. End of quote. He does go on to add a footnote that Gauss's law is actually more general than Coulomb's law. And here was my logic in thinking that, well, there must be a force equation where like charges attract. You know, Coulomb's law says that like forces repel. Okay. So to be consistent with that, Gauss's law must also say that electric forces repel. Okay. Newton's field equations have the opposite sign of Gauss's field equations. So like charges must attract, okay, for gravity. And that must result in a force law for gravity where like charges attract, okay? Now this is not a circle of logic, it's a path. We go from Coulomb to Gauss, over to Newton, to this new kind of force law. And I could say with utmost confidence that my field equations demand that like charges attract. So where was my force equation? I didn't have one. Oh, I mean, I did try a couple of times, but the calculation never worked out. I figured I was doing something wrong. And it was one of those rare times when I actually made a file and put the calculations away. I just knew I would have to do that calculation right someday. And I would revisit it from time to time, you know, like once every 2 years, 3 years. Oh yeah, it's that force thing. Where is that? Damn, still not working. And you know, maybe maybe I was just flopping because I just was not bright enough to really understand it. But the thing, here's the kicker though, that getting the form of the equation is not enough. The same solution has to work between the force and the field equations. Now, I was slow to pick up on that constraint. It's easier to treat them as independent, but that's my own kind of fault. So in this derivation series, several people said the force equation, the one that I had not figured out how to calculate, showed that like charges repelled. So I was like, well, is that true? I don't know. I'm not sure. Well, that drove me to pull out the folder and try again. And last weekend, I was able to see why they said what they said. That using the good old standard derivation of the Lorentz force equation of EM always gives the good old Lorentz force of EM. And if I used my current coupling term, which was the same as that for EM, then I would end up with the same force law. There was just nothing I could do. Nothing I could do. Like charges repel for the Lorentz force equation. That was uncomfortable. That's what sometimes physics is like. It's like, oh, this is uncomfortable. This isn't working. The derivation just always ended up in the house of EM where like charges repel. But the details that bothered me last weekend, as it did every other time I'd done this, was that I got all these, you know, cross products. Why should that bother me? Well, the entire thrust of hypercomplex gravity proposal was that there are these symmetric cross products that take the place of standard cross products. And that just wasn't happening. It never happened. And so I was never happy. Okay? And so, like any thorough experimentalist that I am, I decided to challenge whatever assumptions I could. Now, there weren't many. I mean, it's not like there's big, it's like you start from a really small launch pad, okay? And so I decided to challenge my assumption that the current coupling term had to be a Lorentz invariant scalar, all right? So maybe I don't have the stars on there, okay? And so I erased it, and I repeated the calculation, and I started to see some symmetric curls show up. And so the form was spot on. And too bad there was just no way to find a solution that would work for both of them. That was kind of a bummer. And I should say I was getting kicked around by two people in two different locations, one Science 2.0 comments, and also on a Google Plus, what do we call that, stream. You know, I was getting kicked around, okay? And I call them fair kicks to the groin by these critics, because I could see why they were coming quickly to the conclusion that from a force perspective, you know, they never talked about fields, okay? They ignored my side, okay? They said, on a force side, you are so wrong. I could see how they could see it. Oh my gosh, that's flawed. Okay, and it just took me a while to figure out a fix. Okay, and so that's all I'm going to really present here. I'm not going to go into the details of how we, scratched at each other. Who scratched more than who? It's that doesn't matter. What matters to me is the bottom line, which is how do you solve this problem with forces for my proposal. Okay, so here's how I'm going to proceed. I will derive the Lorentz force for EM, just nice and neat, so that folks who like math can follow along. I will include an extension that actually gets to Coulomb's law. No matter which side of the fence you sit on with regards to my work, the derivation, that derivation will have value, to look at, and or it might be review for you, who knows. I will then repeat the calculation side by side so you can spot both Coulomb's law and the one for Newton, for my Newtonian kind of like proposal. So you can, and you'll be able to, we'll get down to Newton in the end, so you'll be able to see, one next to the other and go, oh, that's how it works. So I should say that Newton actually didn't derive his equations this way. What he did was rely on observational data and said, what kind of calculus equation would solve this? And then that led him to the inverse square law kind of thing. So the derivation series just focused on fields. And this is the way modern physics goes. It's all fields. Forces? No, those are passé. So it was kind of, actually, that was one of the things that took me by surprise. It was like, I really have to get along with those? It's like, I thought fields was everything. It's like, no. Since it's the same thing, you got to be a consistent theory, you have to be able to do both. And I actually had trouble switching back to the Lagrangians for good old particles. Because that's what you actually need to get to the Lorentz force. It's about pushing around a particle. It's not this whole field where everything is everywhere and you got a function that describes it. No, it's like, it's there? Okay, deal with it. So there are really two things that one varies to get to the Lorentz force. That would be position and velocity. And I'm not really going to show you why that's kind of different from the field equation one. I mean, they just look really similar to the standard Euler-Lagrange, but differing in some detail, like using a total time derivative, which is actually pretty important. So we start with the Lagrangian, which is no longer a density. And that is the kinetic energy term and one for current coupling and nothing else. This is some serious minimalism. That V in there is a velocity, and there's a real charge Q instead of a current density rho. And there is this relevant equation that says change in respect to position is going to be equal to this total time derivative with respect to velocity. And this has got the similar structure to Euler-Lagrange equation used before, but it is non-relativistic. It's just a variant. And we do note that that total time derivative, which is an important point. So who changes with respect to space? Good old R. That would be the potential phi and A. Who changes with respect to velocity? That would be the kinetic energy term and the current. So let's just kind of write that out here. And then we see we've got let's take the force over to one side, give it its own private location. Now, we have to take the total time derivative sidebar. And that is that the total time derivative is made up of two parts. One part is the partial derivative with respect to time, and the other has to do with moving charges in space. Now recall the definition of the E field. It's E equals minus dA dt minus del phi. So the changes in space have the same sign as the changes in time. So the total time derivative of A can be viewed as a partial time derivative, as being partial time derivative of A with respect to D, then phi dot del A. The phi dot del is a scalar operator acting on a vector, so it's got the right kind of, I don't know, vectorism, as it were. And then you really do need to know a bit of vector calculus magic. Actually, it's just a fancy vector identity. It goes like del v dot a minus v dot del a equals v cross del cross a. You know, this is one of those things you have to look up. I actually did check that this weekend. It takes took me about 10 minutes. And it's not that easy to summarize. Other than whatever shows up in the dot thing twice, well, that goes first. So that's the end of this sidebar. So let me plug in these partial derivative values for the total derivative of A, and then I use that vector identity and I end up at the Lorentz force law in its non-relativistic form. So that's enough, right? No. That was my own failure until sometime late on Monday. One has to take a phi that when found as a solution to the field equations, plug that into the equations in here, and then show that the Lorentz force law indicates like charges repel. You know, the force is positive. Okay, so the solution to the field equations for EM is, you know, just good old Q over R. Now take the derivative of that with respect to R and you get minus Q over R squared, so that in the static case the force just equals some constants K Q over R squared. Okay, we had that minus, another minus, good. Good old Coulomb's law, first guessed by Joseph Priestley. All right, so now we're going to do the calculation in parallel. All right, so to do the hypercomplex gravity proposal, here is my Lagrangian. Again, it's only a kinetic energy term and a current coupling term, but that current coupling has two minus signs. And there's this important difference that we're working with this small e field, which is defined as the derivative, positive derivative of A with respect to t minus del phi. So this has a sign flip in there between changes in time and changes in space. So, so that's going to be very important. So we see here roll again. They've got the basic definition of Euler-Lagrange in this non-relativistic case. We say what changes with respect to space, the same things change. What changes with respect to velocity, the same things change. Put the force thing over on it on one side, collect everybody on there. Then we've got our sidebar saying that changes in time and changes in space are opposite in sign. And we plug that back in, and instead of getting the typical curl, we're getting the symmetric curl, because everybody in there is positive, okay? And then we end up with this expression. And we've got this phi that we have, and if we make a bunch of assumptions, we end up with Newton's force law, which is good. It's actually necessary. So as I like to say, the ink is still drying on this one based on my previous efforts. It's going to take me a number of weeks for me to come up with a mathematical notebook with that stuff in it. So I wish to thank, actually, my critics who pushed me, believe me, shoved me, to find a solution to the field equations consistent with the force equations. And this process is like rarely pretty in any business. I mean, any You know, how about those nice, pretty iPhones? You know what a jerk Steve Jobs was to work with? You know, but it's so pretty. It's like, yeah, it was not pretty on the inside, okay? You know, but I actually feel like so much better not having that notebook, file in my cabinet. Instead, I have a working force equation. And I'm hoping that, you know, it'll withstand any further attacks. But we'll see, okay? Physics is a contact sport, as I like to say. So here's the snarky puzzle. Show how to derive the Coulomb force equation if you start from Gauss's law. Now, if you get stuck, you can go to lots of different physics books, but Chapter 8-5 of David Holliday and Resnick, Physics Part 2, has the answers if you get stuck. All right, thank you very much.